So now we're going to work on lesson 4.2. Graphing exponential decay functions. Again, when we think of the word decay, think of it like something's rotting away. Well, it's getting smaller. So decay functions are the opposite of growth functions. Instead of values getting exponentially larger, they're going to get exponentially smaller. So some of the examples we'll see is depreciation costs of snowmobiles, life expectancy of medicine, bike costs, things like that. All right, so let's take a look at some key vocabulary. So the exponential decay function, what makes this a decay function versus a growth function? How can I tell just by looking at it? And then the decay factor, of course, being that difference. All right, our first example is graphing y equals b to the x for 0 is less than b is less than 1. So right away, this is what we're seeing as the difference. Instead of b being greater than 1 for the growth functions and our growth factors, that b is this factor. If it's between 0 and 1, then it's going to represent a decay function. Of course, b has to be positive. So for values that are between 0 and 1, those are decay functions. For values of b being greater than 1, those are growth functions. The same process is going to apply when we graph it. Go ahead and make your table of values. I like to start off with 0, 1, 2, maybe take a look at -1, just to get an idea of the steepness of the curve. So when I plug in 0, so again, 1/3 to the 0, still going to be equal to 1, right? Anything raised to the 0 power is 1. 1/3 to the first power is 1/3. 1/3 squared would be 1/9. Notice that as x gets bigger, y is getting smaller. So when we graph this, let's put these points on here. 1/3, right about there. 1/9, right about there. Notice that now we're getting closer to y equaling 0 as x approaches infinity. So if I have -1, that would be 3. And -2 would be 9, way up there somewhere. So as I graph my function, it's the opposite of the growth function. Still has the same characteristics as we're approaching 0, but we don't ever quite reach it. Y equals 0 is our asymptote. So the domain, right, all the x values still the same, all real numbers. And our range is still the same, right, where y is greater than 0. It's just the direction of the graph has changed. Now as x approaches positive infinity, y approaches 0. And as x approaches negative infinity, negative infinity, y approaches positive infinity. So look at the direction when we're talking about our decay functions versus the growth functions. Okay, let's clear that off and take a look at our next example. All right, so now we're graphing where this time we have a coefficient for our function. B is still going to be between 0 and 1, so it's still a decay function, but now it's even greater of a decrease. Because now you have that coefficient. Oops. Let's get this off the mouse and back onto the pen. So now that I have this coefficient, it's going to make the graph steeper. And then if I add negative, it's going to make it flip across the y-axis. Let's go ahead and take a look at A. So y equals 3 times 1/3 to the x power. I'm going to go ahead and set up my table of values here. So we have x and y. Just for simplicity's sake, I just want to do a couple of values here. So -1, 0, 1, and 2. So -1, let's start with 0. I like starting off with 0. 1/3 to the 0 is 1. 3 times 1 is 3. 1/3 to the 1 is 1. 1/3 times 3 is 1. So again, you see that decreasing value as x gets bigger. Plug in the other values, and then graph those points. So -1 up at 9, way up here somewhere, we're not really going to see it. 0, 3, right here. Notice that's 3 times as big as what it has been. 1, 1. And 2 is 1/3. So we're given a little more leeway here. The graph's a little bit steeper compared to our other functions. Oops, I skipped over those points. There we go. But as x gets bigger, y approaches 0. So again, our asymptote here is still y equaling 0. The domain, just like always, x equals all real numbers. And our range is that y is greater than 0. All right? So we're still seeing that same trend. Let's take a look at what happens when we have a negative coefficient, as you can expect. All right, so to give us a little perspective, I'm going to change the color, and let's do our table down here. So again, just a couple of easy numbers. 1/2 to the 0 is 1. -2 times 1 is -2. 1/2 to the 1 is 1/2 times -2 would be -1. 1/2 squared is 1/4 times -2 would be -1/2. And then 1/2 to the -1 would be +2, because you're going to flip them. -2 times +2 is -4. All right, let's graph those values. So -1, -4, 0, -2, 1, -1, and 2, -1/2. And if we were to keep going, we would be noticing that we are gradually getting closer to that 0, y equaling 0, but never quite approaching it. So we're going to get close and close and close, but we're never actually going to touch it. So you'll notice that the domain is still the same. X is all real values, nothing is left out here. And this time, though, our range is different. Y is negative, so these are values that are less than 0. Same as what we did with the exponential function, just the graphs look a little bit different. And the only reason why is this b value. It's between 0 and 1. It's a fraction, all right? Instead of it being greater than 1. All right, let's clear that off and take a look at our next graph. So, same idea. We have these horizontal shifts. I'm going to go back to my blue pen here, because I like it. All right, we have an H and we have a K. Remember, H tells us our horizontal shift. If it's positive, go to the right, negative, go to the left. And K tells us our vertical shift. So, up or down, based on if it's positive, and horizontal is left or right. So, again, first thing you want to do is graph the 2 points of x equaling 0 and x equaling 1 for just the basic function. All right, so let's ignore the h and the k for right now. And let's just take a look at what this would be for 2 times 2/3 to the x. Then we'll apply our translations. So 2/3 to the 0 is 1, so that means times 2, so 0, 2. And then 2/3 to the first power is 2/3 times 2 would give us 4/3. So just a little more than 1 1/3. Let's go ahead and graph those 2 points. So we have 0, 2, and we have 1 1/3. All right, we already know the characteristics of the curve, that it's going to go ahead and curve left to right, approaching 0. I think my calibration is off a little bit. My lines are being kind of squirrely. All right, and then to do our translations, all right, we want to shift to the right. Well, h is equal to 1. I thought I changed this color. Try again. There we go. H is equal to 1. That's not changed at all. should just stick with blue, but I'm going to try. And K, there we go, K is equal to 1. So we're going to shift to the right 1 and up 1. So go to this point, to the right 1 and up 1. There we go. This point was to the right 1 and up 1, right about there. So then let's draw that line. And of course, if we've shifted it up 1, that means we've also shifted up the asymptote. So this line right here is the one that the graph is going to approach, but never quite reach. You'll notice that this always approaches 0, but we add 1 to that. So we're going to have the asymptote at x equals positive 1. So domain, of course, still x equaling all reals. And the range, this time, are y values that are greater than, let's try the proper symbol there, greater than 1. It can get a little messy, obviously, as you see, so please make sure you take the time to graph as neatly as possible. All right, let's clear that off and move to our practice problems. All right, so at this time, go ahead and pause the video so you can see the 3 function questions. Graph the function, state the domain and range. Make sure you follow the steps that I've suggested for you as far as what numbers to start with on your graphing and etc. When you're ready, press play and you can see the answers. All right, so here are the answers to the 3 questions. Again, make notes of any that you have questions on, and we'll cover it in class. Our last example is talking about depreciation. So again, those of you that have been in the business class, this might be familiar to you. We have talked about values. How do you account for this? You buy something new, but next year it's not going to be worth as much. How do you account for that on your balance sheet? So we talked about depreciation. So this is a new formula. Again, you need to memorize these formulas to be able to use on quizzes and tests. This one's a little bit easier. You have the initial balance, which is A, times 1 minus the rate. Again, put the rate as a decimal. So this is going to be a value less than 1, because you're not going to take 100% of something, you're going to take less than that. And then you raise that 1 minus r to some value t, which is basically the number of years. Depreciation is counted by years, not counted by months or anything like that. All right, so let's take a look at our example. A new all-terrain vehicle, also known as an ATV, costs $800. The value of the ATV decreases by 10% each year. Write an exponential decay model for the value of the ATV, y, and dollars, of course this is money, after t years. And then estimate the value after 5 years. All right, so the value, the function is going to be 800 for the initial value, then 1 minus 10%, again, as a decimal, you can say 0.1 or 0.10, it's up to you, to the t value. That's the model. And then to solve it, substitute in, simplify 1 minus 10%, and substitute in 5 for t. Plug this into your calculator, and you get a value of approximately $472.39. Again, US money has 2 decimal places. Make sure you account for that and put the dollar sign in front. All right. Your last exercise is following the same idea, but now we have a different ATV. We want to know what the value is after 4 years if the price was $550 and the value decreased by 7 years. So pause, take a moment to solve the problem. When you're ready, hit play to see the answer. All right, so hopefully you have had a chance to solve that. And the answer is $411.29. So again, if you have questions, please make note and we'll talk about it in class.